All right, then let me get started. So thanks for inviting me today to talk about SYCL Kernel Fusion and the extension that we've been developing for it. As a quick overview of what I'm going to talk about in the next 30 to 40 minutes, first the motivation for the extension, a bit of description of the extension itself, then going to do a bit of a deep dive into the implementation, how it works in the background, how we've implemented it as part of DPC++ SYCL implementation, and then give a bit of an outlook on the future, which is Graph Fusion. So for the motivation, every SYCL kernel launch, or also every CUDA kernel launch, or every OpenCL kernel launch carries some costs with it. There's an overhead associated with that. And especially if you have very short running kernels, the high ratio between your overhead and your actual computation becomes somewhat of a problem, because suddenly you're doing a lot of overhead and you're doing very little computation. And this kind of short running computations can, for example, occur in different domains. And our motivating domain was actually machine learning, where every neural network operator, for example, is mapped to one kernel, and you have a lot of operators in one network typically. And usually a SYCL application is more than one kernel, and that can then lead to a sequence of short running kernels. And now you have always a lot of overhead, a bit of computation, a lot of overhead again, and then a bit of computation again. And what we can do to improve this overhead to computation ratio is just to fuse those computations together. So we take those kernels, fuse them into one kernel, and then we only pay that overhead once here and once here. But we get a lot more computation in one go after fusing those kernels. Of course, it's possible to manually fuse that. So you can take your kernels, you just take the implementation of one kernel, put it behind the other kernel in source, and you get a fused kernel. But that's a lot of work for developers, especially if you think about neural network operators, where you have a large cross product of potential operators and how they can be fused to each other. It's also something that is very error prone, because if you do that manually, you probably will introduce some errors in your code. And it's usually also not possible for kernels coming from a library. So if your library is shipped in binary format, it would be hard to integrate that here. So our idea was to develop an extension for SYCL, the SYCL programming model, to take care of that. So the idea or the goal was to allow the user to instruct the SYCL runtime to fuse multiple kernels. So basically give the user an API to say, fuse those two or more kernels together. The API should be easy to use. It was the goal for the design of the API. And we wanted to keep the user in the driver's seat. So some parts of the correctness of or the profitability of fusing those kernels is very hard to assess with compiler methodology. So if you only have static analysis available, it's hard to determine if you can actually fuse or if it will be beneficial to fuse. So instead, we put the user in the driver's seat, and the user triggers the fusion. That way also takes the responsibility of making sure those kernels can actually be fused safely. The SYCL runtime then completely automates the process of creating a fused kernel, so you don't have to go and take your source code and put it together in a fused kernel. You just instruct this runtime to do it, and then it happens for you. So how does the API look like? So the first thing you need to do is you will add another property called enable fusion to your queue. So if you construct a SYCL queue where you can submit your work to, you will just add this property. The property in itself doesn't do much with the queue. It just is marking that queue as supporting fusion. The next step, if you then actually want to start fusing a bunch of kernels, you create a fusion wrapper, and you call start fusion on that wrapper, and that puts the queue in something that we call the fusion mode. And what does fusion mode mean? If you now submit kernels, so this is abbreviated obviously, but those kernels will not be executed right away. Usually, if you had this queue submit here without fusion mode, the SYCL runtime scheduler will make sure that all dependencies are met and then immediately schedule that kernel for execution. In fusion mode, instead, we do not execute them right away, but we store them in a list, basically. So we create a list of kernels that should be fused in the future. And then actually, when you call complete fusion on the wrapper again, we leave the fusion mode, and from all the kernels that have been added to that list through the submissions between start fusion and complete fusion, we will create a fuse kernel and schedule that fuse kernel for execution. This fusing and scheduling a kernel is all part of this complete fusion call here. So it's all happening in one go, basically. But fusion and getting rid of some of that overhead is not the only thing that we can do if we talk about fusion. We can also do more optimizations, and data flow internalization is an example of that. So we take a very simple example here. We have two kernels. The first kernel consumes two inputs, produces an output that is stored into global memory. And our second kernel will read that output and additional input and produce the eventual output of those two kernels. So now if we fuse the two kernels, we end up with this picture. So we have our three inputs that we had earlier. We have a fuse kernel, and that fuse kernel will first compute what used to be kernel 1, store the result to global memory, and then load from global memory again to produce what was kernel 2, basically, and then eventually store the result. But if you look at this picture, it already becomes quite clear that we can actually optimize something here. And by replacing, for example, these going to global memory and then loading from global memory again with access to private memory, we can get rid of some of the expensive global memory accesses and replace them with much cheaper private memory accesses, or also with local memory accesses, which are still much cheaper than a global memory access. So this is exactly what we want to achieve with the data flow internalization. So we designed an API for that, and the API is pretty simple. It's just two properties. You can either promote to local memory, which requires that your kernels do work group exclusive access, so you don't share data between different work groups of your kernel. Or you can promote to private memory, which is essentially registers on most GPUs, which requires your work items to be work item exclusive access. So no work items, even in the same work group, share data with each other, because the registers wouldn't be available to other work items, even in the same work group. So with this property, the user expresses, okay, this is work item exclusive access. You can promote this to private memory. And then you simply attach these properties either to a buffer or to all accessors for a buffer, and that instructs the SYCL runtime to perform the data inflow internalization for you. Just quick detour. You might ask now, okay, why can't the compiler figure out when to do this internalization? Well, first, again, with only static information, all the aliasing that could be going on in C++, it's hard to figure out when it's actually work item or work group exclusive access, but this could still be done. But what the compiler cannot do is reason about the future. So if you look at this timeline here, we call start fusion, we submit two kernels, that kernel will store to some memory, and the next one will load from some memory. But if we now internalize this memory, the results wouldn't be stored anymore. So the kernel 3 couldn't be loading from that memory anymore. And because at the time that we call complete fusion, the JIT compiler cannot predict the future. So the JIT compiler will not know whether there will be a kernel 3 that needs to read this memory here or not. So with the property, you basically express, okay, it's okay to internalize that. Kernel 3 might be using the same buffer, but kernel 3 doesn't care about the results produced by kernel 1 in this case. So this is the second thing that the property specifies. And this is why we also need this property to not require our JIT compiler to predict the future. So how does this all look in the implementation? It's the high-level concepts. How does the implementation look like? So we have mostly three components here. With a JIT compiler, I'm going to talk about that in a minute a bit more. We have the SYCL runtime, so that's your SYCL implementation. Could be adaptive CPP runtime, or in our case, it's DPC++ SYCL runtime. And that runtime usually has a scheduler that's responsible for scheduling kernels. And then you have your application where you have a queue, and in this queue, you added the enable fusion property. So what you now do is you start fusion, and then you start submitting some kernels, and what will happen, so you submit the kernels, they go to the queue informs the scheduler about these kernels, and the scheduler knows, okay, this queue, because you started fusion, is currently in fusion mode. So instead of scheduling the kernels for execution, we'll just store them in a list of kernels, the fusion list. I'm just going to call them for now. So then eventually you will call complete fusion. And then we come to something that we call the fuser. It's a small component in the SYCL runtime. And that fuser just takes the list of kernels from the scheduler and then invokes our JIT compiler. So what happens here is that what we pass to the JIT compiler is SPIR-V if we're targeting an Intel GPU or an Intel CPU. If we're targeting NVIDIA GPUs or AMD GPUs, which are also both supported, the input format in this case would be LLVMIR. The additional info that we pass in is information about constants, about properties applied to your accessors, for example, and information about which parameters are identical, because that's something after you've submitted your kernels, the fuser can figure that out just from the information that the SYCL runtime has. If the input format was SPIR-V, we will translate the SPIR-V to LLVMIR, and then we have a number of passes that we developed in the JIT compiler. The first one is doing the kernel fusion, the next one is going to do the internalization, the data flow internalization, and then we do some constant propagation. I'm going to talk about each of these steps in a minute a bit more. We also basically run a more or less standard LLVM optimization pipeline on the output of this. And then we translate the output back to SPIR-V if we're targeting Intel devices, or we will translate the output to GCN or PTX if we're targeting AMD or NVIDIA devices. And then the kernel goes back to the fuser, and the fuser can then inform the scheduler to actually execute that fuse kernel. So the implementation, where the fusion happens, is actually a JIT compiler that runs that happens at runtime. It's not a compiler that you invoke before running your application. It's a compiler that is invoked in the background while you execute your application. So you want to take a bit of deeper look at how the JIT compiler works. So the first step, and this is a bit of pseudocode, slightly akin to LLVMIR. So we have our two input kernels here, and we want to fuse them now. So what we do, we create a fuse kernel that has all the parameters of the first kernel and all the parameters of the second kernel. And then for the first step, we simply call our input kernel 1, then we insert a barrier, and then we call our input kernel 2. Okay. So far so good, but in many cases, you might not need this barrier. So what the user can do, you can specify when you call complete fusion, you can pass in a property called no barriers, which basically tells the JIT compiler, okay, I know this is safe. You don't need to insert any barriers. This property is something that we attach as LLVMIR metadata, so the JIT compiler can actually read that. And what it will do, it will just eliminate that barrier, and we have two calls back to our input kernels. Okay. The next step is the SYCL runtime, because it knows all the parameters that you pass in, will be able to figure out if there's identical arguments. So for example, if you pass in this accessors to the same buffer with the same parameters as arguments to kernel 1 and as arguments to kernel 2, the SYCL runtime will be able to determine that. And so we'll attach some bit of LLVM metadata that says, okay, the accessor 3 argument and the accessor 4 argument are identical. So what we can then do is we can just remove accessor 4 from the parameter list, and we replace the use of accessor 4 in the call to input kernel 2 with accessor 3 because they're identical. So it's fine to just replace one with the other. What we can also do is we can propagate constants for scalar parameters. So let's say you have a parameter to your kernel that is an int or a float, for example. The SYCL runtime again will be able to determine, because this JIT compiler is running after you've submitted your kernels. The JIT compiler is now able to determine the value of those constants. So we have this list here, and what we're going to do, we're going to remove the arguments and just replace them with their actual constant value. Well, not having to pass the parameters in is already a small optimization. The real power of this constant propagation optimization actually lies in the optimization that it enables. Because, for example, if the scalar parameter was used as the check in an if, or as a loop bound in a for loop, for example, the following LVM optimization paths that we run at the end of our fusion pipeline would be able to use that to, for example, unroll your loop or completely eliminate that if from your code. So the constant propagation is also kind of an enabling optimization that enables other optimizations to do more stuff. What we do in the next step, we basically inline the fuse kernel functions because calls on GPUs are usually rather expensive. So instead of calling the two input kernels, we just take the body of the input kernel and just put it here. We do the same with the body of the second kernel. So you basically have one body now for your fuse kernel. And then we can do internalization. So the user, for example, has specified that he wants to internalize accessor free to private memory. And this will be attached as metadata again, so the JIT compiler can read that. This translation from user properties to metadata happens when we pass in the information from that fuser in the SYCL runtime to the JIT compiler. There's this small translation step for that. So if we know that we're going to internalize accessor free to private memory, aka registers, we remove accessor free from the parameter list. We can remove this store here, and we can remove this load here. And instead of using this value that results from the load here, we can directly use value 99, which was first stored and then essentially read here again. So we can do this. We have our, value 99 produced by this multiplication, and it's now directly used as data flow or values in LLVM terms directly here. So we now have a data flow from here to here, and it could be in a register, for example. Okay, that's on the internalization. And I want to talk a bit about the future, as I promised earlier, and that's graph fusion. So maybe as a bit of background, because I wasn't sure if you are heard about SYCL graphs before. So SYCL graphs is an extension developed also by Intel and Codeplay together to define and execute graphs of kernels. So the idea here is also similar to what we discussed earlier in the motivation. You want to reduce the overhead if you launch the same graph of kernel multiple times. So you have a combination of, say, 4 or 5 kernels that depend on each other, and you launch them multiple times. So for example, because your application has some loop or there's a recurring pattern in your application. So what you do, you define that graph once. There's 2 APIs available for that. You have the explicit graph API, where you add nodes and edges through an API explicitly. So you say add node to graph, add edge to graph, or the alternative is what in the extension is called the record and replay mode, where you capture the graph by recording kernel submissions to the queue, which is very similar to the fusion mode. So again, you put the queue in some sort of recording mode, you submit a number of kernels, and then you stop the recording, and that the kernels that you've submitted between starting recording and ending recording is essentially the list or your graph. And the dependencies, so the edges, are taken from the dependencies of your kernels. And then once you've defined that graph once, you can run it as often as desired. And because there's underlying graphs extension to runtimes like Level 0 or OpenCL or also CUDA, the overhead for launching a graph is much smaller than for launching each of these kernels individually. But graphs also open the door for optimization. And fusion is one of those potential optimizations for SYCL graphs. So we could, instead of using our own API to define the sequence of kernels that we want to fuse, we can simply use the graph API now. So here's a quick comparison side by side. So on the left side, you see the kernel fusion API that I showed you earlier. So again, pass the property, we start the fusion, we complete the fusion, and the thing will be launched. Right-hand side, you can see the equivalent graph API. So you have a queue that's identical to the left-hand side, just we don't pass the property here for now. We create a command graph for that queue. We start the recording. We submit the same kernels that we submit on the left-hand side. We end the recording. And then we have something that's called a modifiable graph. And before you can execute it, you need to turn it into an executable graph. And that happens through the graph finalize API. And here's where the fusion comes into play. So now we pass in this property require fusion, which just informs the graph implementation. Okay, you want to fuse that graph into a single kernel as much as possible. You then get an executable graph from that step, and this finalize step is also where our JIT compiler would run again. So we can reuse the same JIT compiler that we use for kernel fusion, also for graph fusion. And you get an executable graph, and then you can simply launch that graph through this X1 API graph API down here, which basically informs the scheduler to execute that graph, and the graph will be executed. So you might ask, okay, you have the kernel fusion API. Why do you want to have another API for fusion? And there's a number of advantages that we see in graph fusion. That's why we want to transition to the graph fusion API in the future. Is first thing is one less API that we have to maintain, and is one less API that the users have to learn about. So by unifying the APIs between kernel fusion and SYCL graphs to use the SYCL graphs API for defining your sequence of kernels, we can remove the old kernel fusion API once the transition is complete, and the user doesn't have to learn about an additional API. He can just use the graphs API that is maybe already used to. We also gain something from using this graph API, because before kernel fusion only had something that is similar to the record and replay mode. We now also have a way to explicitly construct your graph from nodes and edges if you want to fuse something. So that's an additional feature we gain for the kernel fusion. And a very interesting point is that before, complete fusion was doing two things. It was creating your fused kernel, and it was also executing it right away. And now with the finalize API, we have this additional step. So the user get an explicit control over when the JIT compilation happens and when the fuse graph is actually executed. And because an executable graph that results from this finalize call can be launched multiple times, you can also now explicitly launch a fused kernel multiple times. So far, if you recorded the same sequence of kernels multiple times and executed that with kernel fusion, the first time we would do the JIT compilation, and we would calculate some sort of hash of your sequence of kernels. And the next time you record the identical sequence of kernels, you would get a cache hit, so the whole JIT compilation process doesn't happen, have to happen again. But of course, if you have an explicit control, you don't need to rely on some cache and us calculating a good hash for you. So that's why we want to transition to this graph fusion API. We're currently working internally on a prototype of that. And then once the prototype is complete, we will bring it to open source DPC++, where it would then be available to users in the future. Yeah, that's almost the end of my talk. I've put together a few references if you want to learn more about kernel fusion. We have written a TACO paper 2 years ago about kernel fusion, so you can download that. It's open access, so you can just go to this URL and download the paper. The actual extension proposal for kernel fusion, so the thing that I showed you first, is under this URL. So it's just an experimental extension as part of DPC++. Sorry, the graph extension, so not graph fusion, just the graph itself, is also an experimental extension. You can find the documentation here. And the graph fusion extension proposal that basically puts kernel fusion on top of graphs is also currently a proposed extension to DPC++ that you can take a look at here. I've also written 2 blog posts about kernel fusion a while ago. The first one was just an introduction of the concept. The second one is much more hands-on, so it demonstrates you how you can actually use kernel fusion. And we also have some implementation documentation, which can also be interesting for users because it describes some of the more intricate details of how you can use this extension and some of the limitations that it has. And if none of these resources helps you with your question, here's my email address. Feel free to just get in touch with me, or you can also get in touch with me through Komuda or Max if you want to. Yeah, that brings me to the conclusion of my talk. So the kernel fusion extension allows users basically to instruct the SYCL runtime, so tell the SYCL runtime to use this for me. I don't want to do it in source. And because Fusion does not only enable to reduce the launch overhead, but also these additional optimizations, and data flow internalization is the most important one here because it significantly reduces memory traffic. In the TACO paper, we have a detailed performance evaluation there. You can see that really the data flow internalization and reducing traffic to global memory is what really gives you performance benefits from Fusion. The implementation is a JIT compiler as part of DPC++. And in the future, we hope we will transition to this Graph Fusion API, which also brings additional features for you as a user. And yeah, well, if you have questions, I can put this legal disclaimer here to make Max happy. And yeah, let me maybe leave presentation mode so I can see if there's any questions.